49? I think number 49 was actually the one that was very similar to what we did in class, right? 49 just said, yo, approximate the fourth root of 624. Well, one way in which we can use differentials, this problem's a little bit boring because it's not really like very mathy, or it's actually too mathy. If you want to approximate this, can you think of a function and a number quite close to 624, which I can evaluate exactly and also evaluate the derivative exactly? Alice. 625. And what's the function?
The fourth root of.
Yeah. So let f of x be the just like fourth root of x function. And we know what that looks like. What does it look like? Yeah, looks kind of like the square root, but like more slowly increasing. And I'm interested in the fourth root of 624, but let's go out to 625, which is extremely close to 624. And thus, if I want to know the fourth root of 624, I could approximate it by using the tangent line to the curve at 625. So there are many ways to do this. I'll just do it the differentials way. Well, okay, first let's take the derivative. What is the derivative? Well, it's like 1/4 x to the negative 3/4. So that's 1 over 4, x to the 3/4. Okay, and when I plug 625, of course, into this, f of 625 is the fourth root of 625, that's just 5. So this is the point, 625 comma 5, 625 comma 5, and what is f prime of 625? Well, it is 125 times 4, is that 1 over 500? Yeah. Is that right?
Yeah.
Yeah. Thus, the slope of this line is 1 over 500, I know now. Okay, so the differentials way to do this problem is to say, all right, I'm not sure what the fourth root of 625 is, but I do know that the fourth root of 625 is going to be approximately equal to, the fourth root of 624 is going to be approximately equal to the fourth root of 625 plus a small change in, or I guess not approximately, it's exactly equal to 625 plus a small, v, plus a small change in, y, okay, yeah, it's, the fourth root of 624 is going to be the fourth root of 625 plus whatever small change in y happened between 625 and 624. And that is approximately equal to the fourth root of 625 plus dy. Okay, and this we know to just be 5. And well, what is dy? dy is just, well, it's just like dy dx basically, right? It's just f prime of 625 times dx. So the answer is that this is going to be approximately equal to 5 plus 1 over 500 times the amount by which x changes from 625 to 624, which is just -1. And thus our approximation for this is 5 minus 1 over 500. So what is that, like, I don't know, whatever that is. 4.998. And if you check that with the calculator, I bet it's like really close to the fourth root of 624. Everyone okay with this? Okay, good. That's all I'm doing on this section. There was also some homework on this. Oh, then you had to watch a video over spring break. It was on the second derivative test. How'd that go? Ethan, let's do one problem from the, I gave you a couple of problems that all involved using the second derivative.
42.
30, 33, 42, 44,
Yeah.
50.
I agree, 42.
42. All right, consensus. 42, oh yeah, this is a good problem. Okay, 42 gives you this function, and the function is 2 sine x
What did you get?
plus cosine 2x. Cosine 2x on the interval from 0 to 2 pi. Okay, so the goal of this problem, just to be straight about this, the goal of this problem is find the relative minima and maxima. How can we find the relative minima and maxima? Well, we should probably take the derivative. So let's do that. So if I take the derivative of this function, I get derivative of sine is cosine, so it's 2 cosine, plus derivative of cosine 2x is negative sine 2x back inside 2. Yeah. So now let's factor this. I can take out a 2, and this becomes cosine x minus sine 2x. Well, for sine 2x, I'm going to write 2 sine x cosine x. Is this pretty much what you guys did? Yeah. Okay, and I can also take out a cosine. So I get 2 cosine x times 1 minus 2 sine x. All right, I took a derivative, I factored it, and now I'm prepared to look at this derivative and tell you what the critical points are. That's going to be where the derivative is 0. Well, when is cosine 0? That's going to happen at pi over 2, at 3 pi over 2. When is this going to be 0? It's going to happen when sine is a half, right? And sine will be half at pi over 6 and 5 pi over 6. Everybody good so far? All right, these are.
Is it relative?
I think I did that right, yeah? Yeah. When sine is 1/2, so boom, boom, boom. All right, now I could, if I wanted to, make a number line for this derivative and see where the sign changes from positive to negative, and then I could know whether these are relative minima or maxima, right? But suppose I'm lazy and don't feel like doing that, making all those like annoying circles and blah 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 blah. Instead, we could apply the bold new technique, the second derivative test. The second derivative test is also a test for finding relative extrema. It just employs the second derivative. How does the second derivative test work? Well, we take the second derivative, and what is the second derivative? Well, I'll go back up to this version. The derivative of 2 cosine is would be negative 2 sine, and then this would, I guess, be minus 2 derivative of sine is cosine 2x back inside 2. So I have this semi-gross thing. Let's see, I can factor this. If I take out negative 2, I'm left with sine x plus 2 cosine 2x. I think I did that right? I did. Alright, so now I have an expression for the second derivative, which wasn't really hard. And now what I could do is, and I guess this is especially useful if you're only interested in like one of the numbers. Like suppose I'm just like, yo, what's going on at pi over 2? And I don't feel like making a whole number line. Just tell me what's going on there. Is it relative min, relative max, neither? Alright, well we can just test it. Take the second derivative of pi over 2, and it should be like not so hard, right? So there's going to be negative 2 times sine of pi over 2 is 1, and pi over 2 times 2 is pi. Cosine pi is negative 1, that's negative 2, so that's negative 1 times negative 2, so that's 2, and that's positive. I'm going really fast, but you guys like this already for homework. This is cool? Alright, what is the significance of the fact that the second derivative is positive here? Okay, here comes the actual thinking. I'm just going to sort of re-discuss the second derivative test for a moment. The idea here is that at pi over 2, I already know that at pi over 2 the derivative is 0. And if the derivative is 0, it means that there must be a horizontal tangent line. Okay. What is the significance of the fact that the second derivative is positive? Well, if the second derivative is positive, concave up, hands under the elephant. That means that all tangent lines lie below the curve. Well, all tangent lines includes this one. So if this line lies below the curve, then the function must look like this, right? And if it looks like that, then that's a relative minimum. So the fact that this is telling me that there is a relative min. You guys basically follow this? You want to do one more? You can do like, suppose I'm interested in pi over 6. Again, you just kind of like do it. What's going on at pi over 6? Plug it in. I get negative sine of pi over 6 is 1/2 plus pi over 6 times 2 is pi over 3. Cosine pi over 3 is 1/2 times 2 is 1. So that's 3/2 times -2 is -3. Yeah, which is negative. I think I did that right? Yeah, I did. So what's the significance of the second derivative being negative? Well, that means that at pi over 6, first of all, it's a critical point where the derivative is 0. Since the derivative is 0, there is a horizontal tangent. But now since the second derivative is negative, it's concave down. Concave down, hands on the elephant. Tangent lines lie above the curve. Tangent lines, all the tangent lines lie above the curve, including that one. Then this must be a relative max. So the second derivative is just another way of demonstrating that a particular, that a function has a relative min or relative max at a particular point. Are we cool? Does it mean we're cool? Give me a thumbs up. Oh, excellent question. If the second derivative is 0, then the second derivative test is just inconclusive, and so you just can't use it. Cool? Sorry. Good, I'm good with that if you are. Last part of the homework, curve sketching.
Number 44.
I think we have time to do like one problem. Which one's for you?
44.
44. Does it change your answer if I tell you that 44 you just can't find the roots and so you just don't have to? You still want to do it?
Wait.
I want to see.
Why not sign it? You can do everything else about it, you just can't find the roots.
Because I was sitting there, I was like,
Wait, so it's always concave.
I guess we're doing 44. So I watched this I made this long video on curve sketching. Was that like
No, it can't be.
enjoyable, annoying, fun, awesome,
Because Ellen is.
whatever?
It was annoying.
Okay, that's
It's very
I didn't even know what I was doing. Like, how?
it's just long, right? At least I did it for you. It would have been more annoying if you had to do it for yourself. Alright, 44 is the function. What is the function? It is the following function. It is 1/24 x cubed minus ln x. Look, I'm sorry, I did not mean to like lead you astray or whatever. You just can't solve, you can't, if you set this equal to 0, you just can't solve that. There are no basic techniques to solve this. We can estimate it using various, yes?
Are there not basic techniques?
Yes, coming up actually very, very soon. But like you still kind of wouldn't do it. You'd use like a technology, but the understanding.
Thank you. Finally, we admit the technology.
Like scissors and levers. Okay, so I was gonna say. All right, no. So staying focused. Let's figure out everything there is to know about this function. Well, first let us do pre-calculus based things, maybe. What seems like a good idea? Yeah. Yeah. Maybe even like domain seems like a good place to start. What is the domain of this function?
0 equals to infinity.
Yeah, I can't take the natural log of negative things, so for starters, like my domain will be from 0 to infinity. How about end behavior? That seems like a good thing to do. What is the limit as x goes to infinity of this function? This is actually not obvious, but common sense kind of tells you what's up.
It's not obvious.
So I guess it is obvious.
Infinity.
Yeah, infinity, because why?
Limit
Because
of
ln goes like-
going like.
Yeah, ln's like, this is, remember we did this whole thing in pre-calc C, this is like the slowest growing thing ever. Natural log is like the slowest growing function ever. Certainly slower than any, the only thing slower is like ln of x, crap like that.
I like log 1,000.
It's growing slower than any polynomial whatsoever. So yeah, this is going to get bigger and bigger, this is getting bigger and bigger also, but like, no contest. So this is infinity. And probably the other thing to discuss is what is the limit as x approaches 0 plus? Because if my function is defined from 0 to infinity, maybe some crazy things are happening at 0, and indeed they are.
Also infinity.
Also infinity, yeah, because this is just 0, but the natural log of a tiny, tiny positive is like negative infinity, right? But we're subtracting that, so this is going to be infinity.
It means that natural log of x is not the slowest growing function ever.
It is the, yeah, it's true. It's, I misspoke. What should I say? It's the
Slowest growing function ever at big numbers.
big numbers, yeah, something like that. Past one.
That's like the fastest.
It's actually confusing. Okay. Okay. Yeah. Let's take the derivative. If we take the derivative, we get 1/8 x squared minus 1 over x. Now we'll employ factoring techniques. I will take out a 1/8 x to the negative 1, and that will leave me with x cubed minus 1, minus 8. Do you guys do something like this? Hopefully. So my factored and thus beautiful form of the first derivative is it is x cubed minus 8 over 8x. That is the first derivative. Okay, what is the second derivative? Well, a wise person would begin from here, thus avoiding like quotient rules when we say it like that. If we differentiate from this spot, we get 1/4 x. That's minus x to the negative 1, so that becomes plus x to the negative 2. Yeah? Okay, and if I factor more, I will now take out a 1/4 x to the negative 2, and if I do such a thing, I will be left with x cubed minus 4 plus 4. Do you agree? Okay, so my algebraically beautiful form of the second derivative is it's x cubed plus 4 all over 4x squared. Okay, I'm so happy. I will now make sign charts to show my happiness. The first derivative is going to change sign at 0 and also at 2, right? If you wanted to be cooler about this, you could write it as x minus 2 x squared plus x, 2x plus 4. You don't really have to do that. You can just kind of be like, yo, this is going to change sign at 2. That's always positive, so the sign chart for f prime, this is pre-calculus really, there's going to be a sign change at 0 and a sign change at 2. Are you guys cool with this? It's like kind of hard, but I mean, we've been building up to this for a while. So, so Calvin, it's like quadratic-y basically, right? Since this is always positive. Sign change at 2, sign change at 0, so it's going to be plus minus plus the first derivative. Nod vigorously if you like did all this and you're like,
Wait.
what? Did I mess up? Yeah, I feel like this is right. Someone back me up? What? Good. Okay.
What's the number like?
What'd you say? Oh, because like 0 shouldn't count. Yeah. I'm still adding it on for, should I not count it? Maybe you're right.
Well, I mean, it's just for prettiness sake.
Yeah, okay. I've changed my mind back again. We'll include it as like, it's like a phantom
Put
limb.
an X over it.
No, I'm gonna get to that in a minute. So the second derivative, where does the second derivative change sign? It changes sign at like negative cube root 4 or something like that, right? What? Negative cube root 4? What? That's not even part of the domain of the function. I know. Phantom limb. And then there's also at 0, it is not changing sign. So the sign chart for this function considered out of context would be negative to positive at cube root 4. Do you agree? You better agree, because I'm right. Alright, now when it comes to superimposing them to make an F number line, now I will heed the wisdom of my students and only begin at 0 because after all the domain of the function is just from 0 to infinity. And it turns out that the relevant numbers thus to understanding the shape of this curve are just 0 and 2. So what is happening? Well, my chart tells me that my function is decreasing on the interval from 0 to 2 and increasing on the interval from 2 to infinity, and in fact that this function is concave up. So this is what I showed you how to do in the video, which is also kind of common sense. If the function is decreasing and concave up, then you just draw a generic decreasing concave up function. And if the function is increasing concave up, you draw a generic increasing concave up function. Now I know what the shape of the curve is and all the relevant intervals. Now I can make a graph of it. And when I make this graph, I see that what?
Alice.
Alice.
I don't know if it's, like when you do this for concave up, that's what the function looks like.
And like above
Yeah,
the
like, go like
elephant.
that.
Like the elephant.
Yeah.
Yeah, that's what.
Yeah, that's why they
I thought it
call.
was just like the tangent line thing.
Yeah, I know. It kind of like it helps. It's the whole reason why I made up this whole story about elephants. Slash, it happened.
I didn't
You didn't know?
No, I didn't realize that.
Oh yeah. Anyway, what is happening? There is basically a relative min at 2, right? If I plug in 2 here, what I get 2 gives is like a third minus ln2. That's going to be negative, right? Because ln2 is like 0.7.
Yeah.
You guys following this? So at 2, I'm going to have a slightly negative number. I don't know where the roots are, and I just have decided to not care. We're going to have a vertical asymptote at here, and so this curve is going to go something like that. What? I guess. I'm not even sure what it looks like that. But anyway, relative min, the part I care about is the relative min at 2. It's concave up everywhere, and like that's it. Cool? Okay, good. Gonna have all this homework stapled all together, nice and beautiful. Put over here next to Rohan. We have. Not collecting the packet because you're gonna work on it more between now and next class. Man, this is good. It's disgusting.
That's probably true. What people use different pages to read.
We need to make more, write more college recs for girls because they always bring baked goods. We didn't bring many baked goods over.
Sorry.
I don't know anything about anything. I don't look.
Could have gone around.
All right, Sandeep, we are now going to discuss something which is a callback to Pre-Calc C. Name your favorite topic from Pre-Calc C.
Conics.
No, why do people like
Conics. Name your second favorite topic from Pre-Calc C.
Polynomials.
Polynomials, matrices. Name your fourth favorite topic from Pre-Calc C.
Conics. Conics?
No,
I don't like those.
Name your seventh favorite.
Okay, that would be
Your
conics.
Notice no one
favorite.
says counting.
Never conics.
Notice no one says counting. We're like.
All right. It's pretty universal that everyone's favorite topic from Pre-Calc C is parametric curves.
Oh, those are cool.
Oh, matrices.
No, he tricked us. He thought he made us think we were going to do comics.
All right.
Rejected that.
So,
It's just throwing.
what we are now going to talk about is the calculus of parametric curves. Raymond, all those parametric curves that we drew in Pre-Calc C, those are really hard. But the answer is that they were really even not that hard because they were all doable with pre-calculus knowledge alone. Sometimes, as you have seen over the last weeks, if we want to really know what's going on, we need calculus to do it. Okay, so we're going to discuss how to analyze parametric curves with calculus right now. We're going to do this lesson really fast. It's like 2 times speed lesson. Are you ready? Samin, ready? Thumbs up. Okay. So, when you have a pair of parametric equations, there's an x equals curve and a y equals curve, and they independently, in terms of a parameter t, describe the motion in the x direction and the motion in the y direction. If we're going to do this problem in general, then I'm going to say that x is some function of t. I'm going to call that function of t g, and y is some function of t. Okay, so supposing I have this setup, there it is, right? And recall that x and y are not functions of each other. X is a function of t, and y is also a function of t. They're independent variables. So in general, if I'm interested in the path that the curve is traced out, it could look like anything, right? It could be some just like crazy woo-woo. There could easily be some parametric curve which closes back in on itself in some kind of wild fashion. All right, and what I'm interested in is talking about what the shape of that parametric curve is. And so, what I want to know is what is the slope for a given t value. What I would like to be able to calculate is the slope of the tangent line. Can you guys just like talk about this whenever it's later? Yeah, good. Right, Fleischman, I'd like to talk about the slope of the tangent line to this curve. And if you think about what the slope of the tangent line to this curve actually kind of means, well, what I mean whenever I talk about the slope is, if I go up a little bit in the x direction by how much will I go up in the y direction, right? Slope of any line is the ratio of the change in y to the change in x. And thus, what I want, if I want to calculate the slope of the tangent line to the curve, what I want is dy dx. Okay. So how can I calculate dy dx? This is getting a little bit complicated because y, like I said, y is not a function of x. Y is a function of t. X is also a function of t. Does anyone know Robert Fleischman?
I think you take the derivative of each with respect to t and you put y on top and x on the bottom.
Yeah, why is that true?
Because it's not, derivative isn't actually like a fraction, but it kind of is. You can remove the, it's not exactly chain rule, but kind of chain rule-ish.
Yeah, actually everything he said is great. In the interest of time, I might actually just skip the real proof and just go right for the goal. Does anyone object to that?
Yeah, no.
Yeah. Okay, so Rabbi Fleischman says, that's hilarious. Rabbi Fleischman says, it's probably true, he says it's probably true that dy dx is just dy dt over dx dt. And his rationale for that is, well, it looks nice, and if I just cancel the dt's on the top and the bottom, then that would actually be true. And since just throwing around these dt's as if they were real things seems to be in fashion nowadays, that's probably correct. And the answer is he's right. And he even said actually more things, which is that derivatives are not fractions. They're limits, but they're limits of ratios. And so they act like ratios, and this is one of the cases in which they act like ratios. So this works. And in fact, we have a theorem which basically says that derivatives act like fractions, and that theorem is the chain rule, right? So this is true because this is really saying the same thing as that dy dx times dx dt equals dy dt. And that's the chain rule in one of its forms says this very thing. Okay. You may or may not find that convincing. Let me do what I was going to actually do two different proofs. So instead, let me do one, the one that's more or less inspired by what he said. But it is essentially what we're going to do is we just eliminate the parameter. So if we eliminate the parameter, then what is that all about? Well, we have, this thing, x is g of t, y is h of t. Let's try, if possible, it's not always possible, but let's just try to express y as a function of x. Okay, yeah, let's suppose that we can actually do that. Let's suppose that we have succeeded in expressing y as some function of x. Okay? Now we can take this and differentiate both sides with respect to t. Everyone do that right now. Yeah, you might even write this as it's really h of t equals fx. Actually, there's a lot of ways to write this. This f of g of t, I guess. This is kind of one way of thinking about it, right? Replace y with h of t, replace x with g of t. Now if I'm differentiating with respect to t, then this is really on the left side, I just get h prime of t, but on the right side I get via the chain rule.
I forget.
F prime of g of t times g prime of t.
Yeah. Yeah. It's just the chain rule. It's really just the chain rule. So rewriting in a slightly different notation, h prime of t is really like dy dt, and f prime of g of t is really just like f. Let's see, what is that? I guess that's just like f prime of x times dx dt. But what is f prime of x? It's just is the derivative of y with respect to x, right? So really this is just, I mean, this is just kind of like a, this is sort of just like a restatement of one way of thinking about the chain rule. Yeah. You guys cool with that? I'm cool with that. All right, let's do a problem. That's the most concise lecture ever on this topic. All right, so, excitement coming now. There's one thing we'll have to get back to in a second. Let's do a problem. There, check it out. I'm going to give you a parametric curve. Harder than any parametric curve I would have given you back in pre-calc C, because it's hard. And I'm going to ask you some specific questions about this curve. All right, so first off, I'll give you the equation. X equals t squared, y equals t cubed minus 3t. Okay. Please make sign charts for x and also sign charts for y so that we can determine when the x is positive and negative and when the y is positive and negative. Alright, so x equals t squared, that's not so hard. This is just going to be positive always, right? And it'll be 0 when x is 0. For y, t cubed minus 3t, we can factor out a t. T squared minus 3, so that's just like, when is this going to change signs? 0 and at negative root 3 and at positive root 3. Okay. So, that seems like a good thing. And oh, it's going to be cubic-y, right? So it'll be like negative, positive, negative, positive. All right. What else is going on? Maybe we should like start to make a graph or something. Make a graph over here. Well, these points, 0 and root 3 and stuff, seem interesting. So let's make some plots. Tell me where I am at 0, for example. Wait, where am I when t is 0? 0, 0. 0, 0, yeah. Yeah, here I am at the point 0, 0, and that is when t equals 0. Where am I when t equals root 3?
0.